Again, dobro jutro. So these are the themes I'm going to look at in this workshop on permanent spray concrete linings. So a lot of you will be familiar with spray concrete, but what I need to do is be able to see the screen. But the focus, of course, today is on permanent applications. And then I'm going to look at some broader topics. Yuri's already mentioned sustainability, and that is going to be an increasingly important part of our work as engineers. I firmly believe this is work that we as engineers should be leading, not looking for somebody else to solve the problem for us. And then I'll go into some of the detailed questions about where can we use this technology, and what are the decisions we need to make in the design process. So, as I said, lots of us are familiar with spray concrete. We've seen it in different forms. I don't know if it's worth dropping the blinds a little bit just to make things clearer. But of course, some of the first applications are in hydropower projects. That's a project from Wales. And then you see the shifting into water tunnels, as an example from Heathrow, or also for transport tunnels. So we all know what a spray concrete lining looks like. What's different about these is that they're all permanent applications. And you see that trend that in the hydropower sector, it's never a question. Of course we use permanent spray concrete. And we have done for, I don't know, probably almost 50 years now. But now we're seeing that trend moving into these other sectors. So why should we change? We have been able to build tunnels very successfully. Why should we change something if it is working well at the moment? And I think there are two key pressures. There is still a pressure on money. Every country has the same problem. They would like to build lots of things, but the finance available is shorter than the demand that they face. And as I'll show you, in some cases, the permanent spray concrete lining approach can be more economic than traditional methods. On a more general level, double shell linings, the traditional approach that you can see in the picture here, can be very wasteful. It depends on your design, of course. The picture here is from a project in London, which is, let's say, a little bit older in style. I mean, there's hardly space to put concrete in between the steel reinforcement there. You can have better approaches, but still we are putting on a temporary lining, which is pretty good quality concrete anyway, and then we ignore it. That is a huge waste. The truth is that we can be producing very high quality concrete in what we call the temporary lining. So can we make use of that in a permanent case? So this slide explains the different design concepts that we have. So we have the traditional, what we call a double shell approach, where you have this temporary lining which carries the short-term loads, and then in the long term there's a sheet waterproof membrane to provide that security against water ingress. And all the loads are carried by this secondary lining, typically cast concrete. The picture of the water tunnel I showed you has no membrane at all. So that, admittedly, it's built in a clay material, so there's very little water in the ground anyway. But that is what we call a single pass system, where it is solely the concrete that is the waterproof lining against any water that's coming in. So that's the single pass down here. And then in between you have options in terms of what we call composite linings. And there's a sharing of the load between the first lining that you spray, the primary lining of permanent concrete, and a secondary lining. So for example, this is the design approach used on a project called Crossrail, which is a new metro in London. So I'll talk more about this concept of composite lining action and so on, and spray applied membranes as I go through this. So I've borrowed this slide from my good friend Carl Gunnar Holter, who's the animateur for our working group. And what Carl's drawn out here is how the technology has changed and how we've reached the point where we can be using this as a permanent material. So there are a number of changes in technology which have combined, and they support each other to enable that to happen. The biggest is probably using wet mix spray concrete. With the wet mix system, everything is batched together at the batching plant, so you know the exact components, most critically the water-cement ratio. So the nozzle man, as he sprays, he can change the accelerator to usually within very fixed limits. That gives you much, much better control on the quality. And that's the big shift from the dry mix through to wet mix. That was probably the most important. You have some changes in associated with that, the way that we spray. We're using much more robotic equipment for spraying. We have some better additives that, of course, the later speakers will talk about. We also see here the arrival of fiber reinforcement. And as most of you know, if we think about durability with reinforced concrete, generally speaking, the problem is not the concrete, it's the steel. As soon as we put steel bars into concrete, that creates a whole new set of durability problems. And that's a critical step that we've made, is to remove steel bars from linings. It's not an essential step, but it can be a way to open the door to permanent linings. So that's where we've got to, where in the last, it's probably now 10, 15 years in some countries, longer, 30 years in Scandinavia, we've been using permanent spray concrete linings. To be fair, we are asking quite a lot from the material itself, and we have to recognize that there is a balancing act to be performed. On one hand, we are spraying this material, so we need to be able to pump it quite long distances. Depending on the logistics, you want the concrete to be alive, available to be used for quite a long time between batching and spraying with a wet mix solution. So it's a demanding application for concrete, but on the other hand, we have very experienced suppliers, very sophisticated additives that can cope with these things. And on the other hand, if we think about the projects we're looking at a design life of 120 years. So we have this demand over a much longer time frame that it should retain its strength, its residual tensile strength, where we have bending in the linings. So we're trying to balance these two things, and that balance is very definitely possible. In some ways, what I'm showing here in terms of the elements of success can be applied to any type of tunneling. You need good materials, good equipment, good people. Beyond that, we also need to have a good environment. If you look at problems on projects, very often it comes back to early decisions and the actual environment. For example, the contract is only awarded on the lowest price. There's a lot of pressure, a lot of competition in the market. Things like that create an environment which can be, which will make it very difficult to achieve the goal that the client has in the beginning. So we also need to think about how we are awarding our contracts, the procurement process. That becomes very important as we look at sustainability as well. So we need to move away from the practice which, to be honest, is predominant everywhere in the world. So I'm based in Scandinavia. If I look at the contracts there, at the end of the day, it's basically awarded on cost. Despite all the pre-qualification and so on, unfortunately, it's usually coming back to cost. And that is not going to give you the best outcome. So we need to look at that as well. So to recap, as I said, there are a number of changes in technology which have combined to enable us to go from this double shell approach to where the industry is heading now, which is basically one composite lining, which may have a waterproof spray applied membrane inside it, but it may not. Depends on the situation that you're looking at. So in particular, it's the wet mix. It's creating that durable concrete that we have confidence that 100, 120 years is fine. There are changes in the way that we control the shape. So that's very important. If you have softer ground or weaker material, you have to have control over that shape and the thickness. And already I've mentioned the fibers and some of the changes in the concrete technology that have come through. And that's all those elements have to be present to put together to create this step from temporary to permanent. So, where can we use this? How do we answer that question? Well, there are a few very simple questions which we can look at, and that will lead us to the answer. So, of course, we start off with the ground. That's a critical component for any tunneling. We need to think about the waterproofing concept. That's usually, in some ways, the more decisive factor. A lot of our tunnels, however, are meant to be drained. So we're not actually putting a lot of water pressure normally on the tunnels that we build. But it depends. There's quite a broad area to look at that, which I'll look in detail. Structural requirements, I can talk about the fibers, and that's, in my mind, relatively easy. Durability is also an area where there's a lot of research has been put in, and this has been demonstrated many times that the concrete which is produced has the same sort of quality, the same microstructure as cast concrete. So we can have confidence that this is a durable material over a lifetime of 100 or 120 years. And also I'm going to be looking at the carbon footprint and touch briefly on constructability, but I think Yuri will go into that in much greater detail later on today. In short, you can use permanent spray concrete linings in most situations, almost all situations in reality. So that's quite a bold statement, and I'm happy for people to come and challenge and come and say, you know, can we use it in this situation? But I think in almost all these situations we can actually use that. As I mentioned, the procurement process at the moment, you're probably familiar with seeing this diagram, and you can sort of draw it and ask a client, you know, what's most important to you? You ask them to put a dot in the triangles, and maybe they say that, you know, we've got a time constraint, so my project is here. It's biased more towards time. But as I said, if you have a pre-qualification process and you ask contractors to submit information about their quality or their organization, we've got lots of good contractors. They all score about the same. And at the end of the day, the decisive criteria tends to be cost. And that is true if we're talking about Norway or Denmark or probably most other countries. This is what we need to be looking at. There are other factors that need to be considered. We need to be thinking about whole life cost. Rather than have a narrow idea of what is the price today just to build, that pushes us towards a situation where people will give you a low price, and then you have lots of problems during construction, lots of claims. And if you look at the final price from those sort of contracts, it is always much higher than the price promised at the beginning. So you have to recognize that if one creates a lot of pressure on price at the beginning, you get a low price, but you pay later. Also, we need to think about solutions might look cheap today, but will they be creating a maintenance problem? Will they be creating costs that you have to pay in 10, 20, 30 years? So whole life costing is a much better way of looking at this rather than just the initial cost that's bid. The environment is also going to become a huge factor that we need to look at. And I'm going to explain in detail what's happening in Scandinavia, which is probably the most advanced in this path. And it'll show you the way our industry is going to go. And this change, I believe, will happen very, very fast. So already in a recent project in Norway that I was working on, one of the evaluation criteria was the embodied carbon footprint for the project. And the way the contract was operated there, that if you bid a price for the overall project, and then there was a reduction in your bidded price, depending on how good your performance was on the embodied carbon footprint. So they're turning that sort of soft parameter into a hard one in terms of cash. They would reduce your price if you had a green solution. So we need to be thinking about these. So we need to be looking at these other parameters, and you can see different types of contract, particularly say in the UK, where the amount of points that are awarded for cost is less than 50%. So they're awarding projects based on other factors, such as, let's say, the organization, the quality, the safety performance, and very soon the carbon content, rather than purely on price. So those are the simple questions in terms of what we're looking at. And as I said, I'm looking more at the exceptional end of sort of the picture rather than the general. So if I'm thinking about the ground behavior, is there something very extreme? Because that's the only area where you can't use permanent spray concrete. You can use it in soft ground, weak rock, hard rock. It's only when you have extreme cases that you're not going to be able to use it. Same for durability. In most of the applications we don't have very aggressive groundwater. We don't have some sort of chemical attack or biological attack. So if you do, then we have to look more carefully, but generally it's not a problem. In our working group, we spent a lot of time talking to the different countries we have involved and trying to gather some information about where this has been used in the past. So this is a little bit old by now, because we did the survey perhaps 5 or 6 years ago. What I found interesting about it was how widely this is spread around the world. So we're familiar with certain places where permanent spray concrete has been used before. Brazil, for example, there's a few projects in Germany, some in the UK. But actually there's quite a lot in Japan, for example, on the railway sector. A lot in Australia, and some of you have perhaps worked on Australian projects. So it's quite a broad spread around the world. And also a very broad spread in the different sectors. So as I said, you traditionally see permanent spray concrete start in the hydropower sector, but you're seeing it applied in every single sector you can think of, from power cable tunnels through to water tunnels, metros, and so on. In terms of linear kilometers, I'm sure our estimate is way under. I mean, it's in the thousands of kilometers rather than hundreds, but we didn't necessarily have the data to back that up. And another reassuring thing, if you're new to this field, is there's quite a lot of information available for you to rely on. We've, along with Wolfgang and Carl Gunnar in the working group and ETTech, we've produced a guide. So that's freely available on the ITA website, looking at permanent spray concrete. And we've included in that some different projects that have been used in a range of geographies, a range of ground conditions and types of tunnel. So the idea is that will give people inspiration. They'll see something there that looks like the tunnel they want to build, and then they'll be able to look in detail through the reports at the technical issues and see how it can be applied in that particular case. So plenty of information available there in terms of specifications, right the way through to sort of design guidance as well. So now I'm going to talk a little bit more about the carbon footprint of tunnels and what's happening there, and why that is going to become a very important part of our work as engineers on a daily basis. So our impact on the environment covers a lot of different things. And at the bottom, you can see the list that's typically considered in what's called a life cycle analysis. So yes, we have this very broad impact on the environment. I'm just going to talk about what we call greenhouse gases. And in simple terms, all the greenhouse gases get converted into an equivalent carbon dioxide impact. So most of you probably heard about the concept of the carbon footprint. So that's a measure of how much equivalent carbon dioxide has been emitted to create an object. So carbon footprint calculations will become a normal part of our work, just the same as calculating the cost on a project. That is absolutely going to happen. So all this discussion will be about the carbon footprint rather than the other impacts, just to keep the conversation short. So to adapt Bob Dylan's comment, the times, they are a-changing. This is changing very fast. So I'll tell you what's happening right now today in sort of the north of Scandinavia and show you how that's changing around the world. So if you think about Norway and Sweden are probably the most advanced in this. The main clients, whether it's the railways or the roads authority, they have this built in to their procurement process today. And what happens is, typically there is pressure from the public, so the government then decides, okay, we will reduce the carbon footprint. And you'll see that the sort of reductions that get stated by governments are big. 40% compared to, in this case, from 1990, this could be even higher than that. So they're looking for everything that the government is involved in to have the carbon footprint reduced by 40%. That then goes down to the ministries, and to be honest, they don't really know what to do about that. So they just give it straight down to the next organization below, the road authority or the railway authority, and you say, reduced by 40%. And that gets passed on to the contractors, reduced by 40%. So now it comes down to us. How are we going to do that? And this is the really interesting problem for us, the challenge for us as engineers. Because today, basically we're building tunnels the way we did 20 or 30 years ago. So it's a little bit better than 1990, but it looks pretty similar to the sort of technology we used before. Double shell linings, maybe the lining is unreinforced, not reinforced, but basically the same. So that tells us that we can't continue to do what we did yesterday or the year before or 30 years ago. It will never be 30 or 40% better than it was before. So if I go back, this is built into to the procurement process, as I said. Every project above a certain size has to have a carbon footprint. And the great thing is the Norwegian Road Authority, for example, has a freely available carbon footprinting tool. And that's aligned with their procurement system. So the same codes for each piece of concrete. You can just type it, your bill of quantities, you can put that straight in, you get the answer very quickly. So that's quite a well-developed system. They're looking at more general impacts through what's called CQUAL, which is a sort of a general environmental assessment that was developed in the UK. And then they're even looking at trying to have what they call emission-free sites. So everything on that site is either powered by electricity or by hydrogen. And they have had a first example, a relatively short water tunnel, which was emission-free. Of course, it depends on how you're generating your electricity, but in Norway, it's predominantly hydropower, so they have very, very green electricity anyway. Let's look at Sweden. Again, Trafikverket, which covers everything that's a rail or road project. It's mandatory to have a carbon footprint. They've gone further and put in contractual requirements on the reductions. So if you meet the target, you get a bonus as a contractor. If you fail, there's a penalty. And so they're moving into this, it's no longer just an ambition. In most countries, in the UK, for example, it's all talk about ambition. But ambition is it's all blah, blah, blah. You don't have any real impact unless you have a carrot and also a stick. So that these carbon footprint calculations are backed up by what we call environmental product declarations. And that tells you for a certain quantity, let's say a ton of reinforcing steel, how much carbon has been emitted in the production of that. And that's the way to check the calculation. You're validating those numbers because those numbers are produced and checked by external authorities. So EPDs become very important. You need to be critical as how you evaluate them. It does put a burden on suppliers. It's quite expensive to create an EPD. And therefore we need to actually support that process to recognize that cost. So finally we come to Denmark, where I live at the moment, and to be honest, Denmark is behind the others. But again, it shows you how the plan, how this process changes. We only passed a climate law in 2020, so it's quite late compared to some other countries. But you can see how fast the change is. So having decided that we have a climate crisis and that the government should do something, that goes into sort of a high-level law. And very quickly, they've decided that they need to reduce, I think it's by 70% from 1990 levels by 2030. Sorry, by 2050. 2050 feels like a long time away, but that target will be broken down into interim targets. So for sure there'll be something by 2030, 2035, 2040. When you look on that level, 2030 is close. So we need to be doing something now if we're going to hit any targets in 2030. Again, if you look at the overall country, and Denmark, thinks of itself as, very environmentally responsible and so on, we've only reduced our overall national impact by less than 40% relative to 1990 levels now. So that the challenge to go to 70% by 2050 is huge. So we need to be looking at anything we can do to make a change, and it applies to all sectors, not just power generation or agriculture or something like that. So that's why even we might feel that we have a very small part of the problem, a very small responsibility. That does not matter. We still need to look at where we were in a sort of our normal behavior, the 1990 style, and we need to reduce to meet our responsibility. So what can we do? As I said, business as usual, that is not going to work. What I'm showing on the left is a typical carbon footprint. This happens to be a high-speed rail project. And this covers the actual operational phase and maintenance and so on. So that's based over a 50-year life in that particular calculation. You can see how much effort is involved, emissions related to actual construction equipment. This is the really interesting area. So with any sort of problem, you look at what's the big stuff, and it's materials. It's materials, materials, materials. We're going to come back to that again and again. If you look at a road project, this is sort of Norwegian data. Again, you'll see it's the construction process is much more important, because the actual operation of the road has less emissions associated, and materials, getting them onto site and producing them is more than 50% of the problem. So if we look at the things we can influence in our general engineering, so we'll leave operations aside, we think about the equipment and the materials and the design. So the good news is that today we can have zero emissions equipment in the sense of it's not a diesel-powered engine. We can have electrically powered equipment. We're pretty good in tunneling, actually. A lot of our equipment already is electrically powered. Tunnel boring machines, ventilation. Nice example here from the Normet company, which has an electrically powered spraying robot. And it's a mixture. It can be battery powered or run off cables and so on. So basically the future is now. All the big equipment suppliers are producing different types of equipment. Some of them are looking at hydrogen power, because to be honest, batteries have a limited lifespan, a limited working sort of period, particularly in cold weather. So hydrogen, I think, will be quite a good option. So these all exist, and that's a picture from this the first emissions-free project, which was run by Statkraft in Norway. The downside, of course, is the cost of that equipment. So that's something we need to recognize. We can't expect contractors to go out and buy this equipment for one project, especially not if it's bid on price. It's simply not economic. You can look at biodiesel. That's adds a lot less in terms of cost, but that's not really. That's what we call a bridging technology. That's a short-term bandage. It's not really curing it. So there's going to be an increase in cost related to equipment, to have a green solution, and that needs to be recognized by us as society and in turn by clients. If we look at materials, there are lots of things we can do in relation to materials. Of course, we can try and waste less and recycle where possible. But to cut everything very short, the easiest, quickest, and most significant change we can make is in design. So there'll be lots of, and I'm sure the next speaker, Wolfgang, will tell us lots about what we can do in terms of changing the actual embodied carbon in some of the materials we have. We can look at alternative materials, and that's quite exciting, and some of it is available today, some of it will be available later. But right now, if we need to make a sort of significant change, it'll be in the design. Before I get on to that, looking at sort of recycling, we have already been looking at recycling aggregates from excavated materials. We've been looking even at using rebound, so the concrete that falls off the wall when you spray, incorporating that as aggregate. So that's been, let's say, that's proven technology. Some interesting things coming out now. What I didn't realize was that in all the tires on the cars, there's steel wire, along with also polypropylene fibers. And the steel wire is a very high strength steel. So there's a project looking at recycling that and then turning it into steel fibers. And it looks as if that they could produce a structural performance that is as good as a lot of the steel fibers on the market at the moment. But of course, this is taking a waste material and turning it into something we can use now. So there's a much lower carbon footprint. So there's some quite exciting research on new recycling. If we think about materials in general, there's a concept called food miles. So if I go and buy some strawberries today in Slovenia, they probably weren't grown in Slovenia. They've come from South Africa or South America. So there's a concept as a person that we can think about food miles. Do I buy those strawberries in November, or do I just accept the fact that I need to wait till May or June before I can have fresh strawberries from a local supplier? We need to take the same approach to the materials. Does it make sense to be taking steel, in particular, from halfway around the world, produced using very dirty technologies, and using it in our construction today? So yes, it is cheap. It's cheap because the polluting effect is not accounted for in the cost. The transportation by shipping is not accounted for. But we need to think about materials miles and reducing that. The more locally we can source materials, the better. Of all the materials we encounter on a construction site, let's say it's a road project, basically we're looking at concrete, asphalt, and steel in that order in terms of significance. So let's forget about the asphalt for the moment, and I'll come back to steel. But if we look at the concrete, this is the biggest contributor we face. And you can see why, because we spray a lot of it. As I think Yuri said, you're looking at 500,000 cubic meters of concrete in the years to come. Huge amounts of concrete we're going to use. Within the concrete itself, it's the cement. At the end of the day, that's the biggest contributor to the carbon footprint. And it's also, you can see straight away, it's the hardest thing to deal with. So I'm very much looking forward to the next talk, because I'm hoping that Wolfgang will tell us that this problem can be changed quite quickly. But for me, not knowing that, my instinct is it's quite hard to reduce this, because we have this balancing act. We need early age strength, we need a long-term performance, and traditionally we have used cement as the solution to that. So we need to look at cement replacements, but that's quite tough to be doing that. Partly in the context of spray concrete, because we need to accelerate the binder to be able to get the early age strength. So I'll let Wolfgang tell us more about that. But what I've done is to look again at this question of design. And if you take a typical, I'll take this example here of a Norwegian tunnel. It's hard rock, obviously, it's drill and blast. You have rock bolts, you have a spray concrete lining. That's a permanent spray concrete, obviously. That's everything in Scandinavia is permanent spray concrete for rock support, fiber reinforced. They don't have any waterproofing membrane. So they rely on pre-grouting the rock to keep the permeability down, so there's very little water coming in, but you still get some water, and there's a danger that forms ice and would fall on the road. So they basically have this structure inside, which is effectively an umbrella. That umbrella, particularly if it's insulated to stop the water freezing, is a huge impact on the carbon footprint. So what I did was to look at the footprint with some different solutions, and here we're using a composite lining. So we have this spray-applied waterproofing membrane inside, and that's the barrier on top of the pre-grouting to stop the water coming in. So that's been trialled very successfully on projects in Norway. It's not something you can use if you've got a very extreme sort of climatic exposure. So at the portals of tunnels where you've got a lot of frost, very cold temperatures, obviously in Norway, it's not suitable. But in the middle of a tunnel, the temperature is actually quite stable. And you can see there's a significant difference compared with the standard. I've also included here a double shell, which in a sort of engineering sense would be crazy to put in a hard rock tunnel to when you have the stable conditions, you have the bolted permanent spray concrete, why would you put a secondary lining in? But some people think it should be done in that context. Because of that secondary lining, there's a massive change in the carbon footprint. So that change in design is something simple that can be done today and has a very, very quick impact. And if you remember back to some of the slides, the road authority in Norway is looking for savings of 30%. And straight away, with a change in design, we can get 20 to 25% saving without having to do something that's reducing the performance or increasing the cost of the overall project. So I've just realized I'm not, sort of a little bit behind on the questions that I asked at the beginning. So I started off by saying we should look at the ground loading and basically use permanent spray concrete in any situation where you don't have an extreme loading. And by extreme, I'm talking about rock burst, which you get in very deep situations, or squeezing conditions, which you can get in more shallow conditions. And I'm sure there are examples of squeezing rock in Slovenia, for example. So I say that you can't use it in those conditions, but actually, these are pictures from the Trajne tunnel, which is a permanent spray concrete lining, so permanent rock bolts, permanent spray concrete. They went through quite severe squeezing ground in some sections. So you can see the damage being done to the primary lining here, that sort of typical cracking behavior. But what they did then was, once the deformation had stabilized in the classic NATM sense, they came back and they put in an inner shell of permanent spray concrete. So even in that condition, although the design is slightly different, they're not including that first lining as part of the permanent works. They are using sprayed concrete as the permanent lining, which, when you have a drill and blast section with a rough surface, of course, saves you a lot of materials. So possibly, even in extreme situations, can be used. Durability is a key concern for clients, and a lot of the projects I've worked on with permanent spray concrete linings have a design life of 100 to 120 years, which is very typical. And I've been involved in different projects with lots of testing, and where you've taken samples and checked them. This one I think is from Crossrail. So even when you have steel bars, you can spray permanent concrete. You can encapsulate those bars and make sure that they're protected against attack from corrosion. It's more difficult, it's quite hard work to do, but it is perfectly possible. the sort of exposure, you just apply the normal rules. This is all standard design. You follow Eurocode 2, you look at those exposure classes. I've basically adapted this, this information from the Norwegians, giving a minimum thickness that's recommended by their road authority, depending on different exposure classes. So for me, the durability question has been answered. With the technology we have, the equipment, we can produce concrete which is as durable as cast concrete. In terms of its performance specification, again, that's quite well described in different documents. Perhaps the numbers are not necessarily written down anywhere, but we need an early age strength class, which we can achieve. The long-term strength doesn't have to be too high. If you think about a lot of our designs, they're not, you don't need very high strength when you have a relatively thick lining anyway. So we want to actually avoid getting too strong concrete. We can achieve that sort of permeability on samples. This is a sample which I show my students, and I place a bet with them. If a student can find the joint, then I'll buy them a pint of beer. And so far nobody has spotted the joints. This was a sample we took from the project in Heathrow, where we deliberately cored through joints to see is that an area of weakness. But of course, it's much better if we can use fiber reinforced concrete rather than bars. Straight away you've eliminated the major durability risk, and you've made your life so much easier in terms of the actual construction. So to turn to fibers, quite a big topic. I'll talk about it tomorrow if anybody's attending the conference. I guess in summary, the good news is that it's well-established technology. Quite a lot of guidance produced, again, from Etatech. You'll find we did a report on the precast concrete segments, and then separately, Stefan Bernard and I have written a paper which is freely available on the fibers in permanent spray concrete. The key advantage of the fibers is that they're so small that even if they corrode as a steel fiber in a crack, you don't get the spalling, the cracking, the pieces of concrete falling off that you see with steel bars. So there are huge amounts of fiber reinforced spray concrete used in the civil engineering sector, particularly Scandinavia. But as our survey showed, all around the world, from Japan to Australia to Canada. And if you look at the dosages of fibers that we're using, typically sort of steel fibers 30-35 kilograms, compared with the sort of reinforcement we have, where you have a lattice girder and layers of mesh, which might be around, let's say, 70-80 kilograms per cubic meter of concrete, straight away we're also saving carbon. So the fibers I'm talking about, predominantly talking about structural fibers, so it could be the macrosynthetic. So those fibers can compete with the, let's call them normal steel fibers. There is a trend, if there are fiber suppliers in the audience, I hope they'll forgive me, but there's a trend to say we need to have more complicated fibers, higher strength. Most of the tunnels I've worked on, the vast majority of the tunnels we've built with fiber reinforcement do not have that. So I would question whether we really need this. There's some cases where we do. And asking that question then also opens the door to some new materials which have lower carbon footprints. Basalt fibers, for example, could be quite an exciting area to look at. They can have quite high performance, but also these recycled tire fibers. So we're using a waste material. So there's some interesting areas there. So yeah, to wrap up in terms of durability, we know we can get the quality on the small samples. So there's a summary of data looking at the permeability, where you take a small sample and you try and push water through that, and you can see how good the permeability is. So it's less permeable than the ground around you, and you can create very durable materials. Waterproofing. So waterproofing is quite a big subject, and what I've tried to summarize in this chart is the range of cases we're looking at. So from the top of the chart, you have a situation where the ground is dry or there's a low permeability. And then we're going from left to right in terms of water pressure. So in a sense, you're getting more available water down this end and a dry situation. And the purpose of the chart is to try and explain which solutions you can use in which areas. So the sort of permanent spray concrete, spray apply waterproofing membrane technology, it's been used in this sort of area here. So situations where you have a low water pressure, where you have largely impermeable ground, like a clay stone, a clay, a pre-grouted rock mass, and low water pressure. That's the interesting area for us. Of course, if you've got a lot of water, high pressure, you want a fully tanked solution, then you use a waterproof membrane and a cast lining. So this is not an answer for every solution, but there are a lot of tunnels you can think of where this is very suitable. Across the top, I've also put the sort of the typical criteria for dryness, and this is why you can imagine that for like a cross passage, where it's an emergency cross passage, that has a lower criteria for dryness compared to a station, for example. Spray applied waterproofing membranes is relatively new technology. Maybe it's 15 years old by now, probably. And it has over those years has matured and is now accepted as a proven technology. And if you look at the projects that have adopted it, the Crossrail project I will talk a little bit about soon, there we're using it on every single station, every single mined station, except for one, for particular reasons. So it's used as accepted for a 120-year design life. It's great on relatively complex situations. You can imagine a station, you've got lots of cross passages, complex geometries. It's a nightmare to put a sheet membrane on. And as I said before, good for low pressure environments. And like permanent spray concrete, there is plenty of available information if you're interested. So again, a Neatotech report, free to download, goes through all the different aspects from design through to construction, and even a draft specification, I think, at the back of that document. Different types of products available, but the best are typically an EVA polymer, which has to cure, has to sort of form the bonds where the polymer knits together. So it takes some time after you apply it. It's applied very simply by spraying. This is a test from a project in Norway, a railway tunnel. The surface preparation is really important. So you can't really spray on a surface like that. You need to put on a smoothing layer so that it's easier. But it's a little bit like painting. You'd never paint that because you just use too much paint and you get holes in it. You need to have a relatively smooth surface. There's an extra construction step involved. One of the weaknesses of the system is that it has to be basically dry before you apply the membrane. So it's a little bit ironic that we're putting on the waterproofing membrane, but it has to be relatively dry before put that waterproofing membrane on. But if you think about a typical rock tunnel, as you drive the tunnel, you're dewatering the area around the tunnel. Whereas in the permanent case, we want to put up something that's impermeable as an arch, and then the water pressure to a degree comes back. So an interesting option for managing those small amounts of water is this drainage mesh that's sort of relatively new on the market. If you have an isolated crack, that's quite easy to handle. You drill into it, you inject it. That's straightforward. It's more to deal with a situation where there's a little bit of water coming in a lot of different places. Too expensive to grab that, but the drainage mesh should catch that, and you can embed it inside the smoothing layer that I mentioned earlier, and then put on a waterproofing membrane on top of that. But also there might be situations where water ingress is less critical, where maybe this is an inspection gallery for a hydropower project or something like that, where this technology could be used on its own. So there's some new innovations coming along in terms of waterproofing as well. Just to let you see what does it look like, this is it's an access tunnel, emergency access to a railway tunnel in southern Norway. That's the final product. So they've had the primary rock support with its permanent rock bolts, sprayed on the membrane, and then covered that over with spray concrete to protect it in the long term. And it looks very good. So just to turn to design. I've mentioned Crossrail several times. It's a project I've spent quite a lot of time on. This is a picture from one of the typical tunnels, very big. It's predominantly constructed in clay, so the clay is relatively impermeable. You're talking 20, 30 meters depth, but there is water in there. And we have to remember this design life is 120 years. These are all public tunnels, so you'll come down an escalator in this particular tunnel, and then you go through a cross passage to get onto the platforms. So we adopted this design for public areas. So that's the highest criteria in terms of water tightness. Excuse me. The actual project itself, I won't talk in great detail because it's too big a project to look at, but in the center, it's all underground. There are 5 stations built with spray concrete linings, and of those, of the 6 stations underground, 5 of them had a spray-applied waterproofing membrane, and all 6 were permanent spray concrete to some degree. The choice being based on waterproofing requirements. So a few pictures from construction from my good friend Ross Dimmick. So that's applying the membrane. Different products used in different stations. I mentioned procurements at the beginning. The contracts on Crossrail had a 3-stage process: pre-qualification, what they called an optimized contractor involvement, where the preferred contractor worked with the designer for 3 months to bring in his ideas, and then the final price from the contractor. And interestingly, for those 5 stations, the different contractors could look at anything they wanted and change it, but they still stuck with the permanent spray concrete and the spray-applied waterproofing membrane. Because on those relatively short structures, they're 250 meters long, lots of cross passages, the costs analysis showed that the permanent spray concrete was more effective than having a steel shutter, a traditional 2-pass cast in situ concrete lining. So as you can see, these are big structures. The platform tunnel is 10 meters in diameter. We also use it for crossovers. And that's how the final structure will look. There's an architectural cladding. Behind that is the permanent sprayed concrete. So the design approach we used is this composite approach, where a certain amount of the ground load is applied to the secondary lining. Composite lining design is a subject that's been debated a lot. To summarize that discussion, it's only really applicable where there's a change over time. So maybe there's a change in ground loading. And that's the case in London in a clay. It goes from an undrained to a drained behavior. So you have a change in load over time that it increases. Or you have a change in water pressure, for example, over time. So those are the cases where you might want to use a composite lining approach. If you don't, if you have a more traditional rock tunnel, personally, I don't see a value in using a composite approach. I would use a slightly different design approach. And the reason I'm saying that is it comes back to the behavior of the membrane and the properties you need to assume. If you're assuming a composite action, which I'm sure you can imagine you've thought about in other sort of structural senses, you're relying on a bond between the 2 objects, which transfers in shear, stresses, and potentially also in tension. And at the time of Crossrail, we didn't have the confidence to include the shear behavior or the tensile bond. Whereas now I'd say we're pretty confident that the tensile bond is fine, but the shear behavior varies. So what I'm trying to look at here is composite action. So at the top here, it's glued together. It's completely one object. The 2 layers work together as one object. And then as you go down to this end of the diagram, they're more independent. The two rings are sort of slipping inside each other. And these are the range of sort of stiffnesses. Sorry, and the axes here, this is the normal stiffness of the membrane, and this is the shear stiffness. So if you look at the published data from the tests, it's in this area. So it's largely working together as a composite if the material is dry. But the problem comes is over 100 years, the water will seep through that primary lining and will saturate the waterproofing membrane. When you look at the longer term properties, the allowing for creep, allowing for the water, the saturated samples, it changes. And for me, that then puts a little bit of a cloud. As a designer, I have to look at the full range from the best properties down to the lower properties. And to cut a very long story short, when you've done that, you realize that either it's working completely as a composite, which is just what we want, or it's sort of halfway in between. And you end up designing to the worst case, and you lose a lot of that composite action. And this is where, again, with Ross, I've looked at having a different concept and questioning what are we actually trying to achieve? What do we actually want? So we have the experience of Crossrail with its major projects, composite lining approach, but still we ended up with very thick linings. And I believe we can push that much further in design and really reduce the secondary lining. So we started asking ourselves, what would we have in the ideal situation? Obviously, everything has to be permanent. There's a big design assumption about where this water acts. If it acts here or here, it can have a big influence on the structural design of this inner lining. So what you have here is the primary ground support, this smoothing layer, regulating layer I mentioned, spray applied membrane, and then something inside. So the question is, what is the thing inside? What do we need to do? And we know that this is glued together in the tensile strength, and we can rely on that bond, let's say half an MPa, maybe much higher than that in actual fact. So in structural terms, if we think about this composite beam, we have a water pressure acting on it. Whether that water pressure is acting as pushing this inner layer downwards or sitting on top, structurally it's the same thing. It's a uniform distributed load acting. So if you assume that it's acting on the top and this is all glued together in the tensile with the tensile strength in the normal direction, then your design becomes much more simple. You put the load effectively on the outside of the primary lining. So that simple change enables us to really reduce this final layer down to the bare minimum. And that gives us something that's very easy to build. There's very few construction steps. And the secondary lining inside is non-structural. So what do we actually need a secondary lining for? So we might need it to have aesthetic requirements. We might need it to give a sort of a protection to the membrane. We have fixings for cables and light small fixings. So that's where we sort of come up with the idea that you only really need about 75 millimeters to provide that. And you can end up with a much more economic design and a much lower carbon footprint. So this is taking a platform tunnel in Crossrail, 10-meter diameter. This was the lining, and as you can see, that's pretty thick, almost 800 millimeters. So there's a lot of concrete involved in that. Taking this approach, we would be able to reduce that by about 40%. This is just showing some work I'm doing at the moment in Cambridge, looking at junction design. Again, it's an example of how we can use better design methods to improve what we're doing. The picture I showed you earlier of these junctions, we deliberately tried to build thick linings to avoid putting in steel bars as much as possible, but we still had to put in a fair amount of steel bars. Typical design methods are elastic, and what I've been doing is remodeling this, looking at the actual performance using a non-linear model. And that that is showing with this information that potentially we can use, we can get rid of the steel, for example, at those junctions. So I think the only thing really to take away from that work is if we use better design methods, we end up with smaller impacts, lower cost and lower carbon. Very quickly, hard rock, it's pretty simple in the sense that we have a queue system, so it's, as I say, it's the standard in Scandinavia. If you have a hard rock situation, use the queue, you know what your permanent lining will have to be. Examples here, this is from a station in Norway. Carl Gunnar's lent me this picture. You can see in the background that sort of inner lining type structure, the traditional approach, and you can see we're actually making the tunnel about a meter, maybe 1.5 meters bigger than it has to be. So we can actually reduce the size of the tunnels by using this. Their approach is systematic pre-grouting. In other countries, you might be looking at using spray-applied membranes instead. Alternative, of course, again, this is Farina tunnel. You can see there they've just used the spray concrete as the impermeable layer. And there'll be, in typical alpine fashion, there'll be drainage in the invert for those tunnels. Workmanship I won't really talk about, as I'm sure Yuri and Zvonko will talk about that much better than I can. But we're going away from the old style hand spraying. These days there's a lot we can do in training using virtual reality, which is obviously a lot cheaper than spraying cubic meters of concrete and going through that process. So there's a huge amount we can do to lift the level of skills that we have in our industry, and that can be done relatively quickly. Bars I've talked about already, so I won't discuss that much more. So just to wrap up, and I appreciate that I'm overrunning a little bit, but I've got 5 minutes. Yeah. So I'd like to walk through an example of where we've gone from traditional approach to a permanent spray concrete lining. So this is, let's say, a very typical situation. It's a road tunnel. This is in the south of England. It's short. The traffic used to go through this village and then obviously get stuck in the middle of the village. Lots of pollution, lots of disturbance. Very simple, a tunnel to go on the blue section underneath this hill. So it's a relatively shallow tunnel. It's short, 1.8 kilometers, twin tube, all the usual road tunnel design. In terms of why did we choose permanent spray concrete, why was it possible? The key thing here is the groundwater table. The blue line here is generally below the tunnel. So of course it rains a lot in England, and all that water is coming down through the ground. This is basically a sandstone, so it's very permeable, but it's a low pressure environment. It's transitory water, so it's a weak sandstone. It's quite competent ground, and it's above the water table. And this is actually going back quite a long time, so it's 2009. And again, you see this combination of innovations coming through. The in terms of controlling the shape of the tunnel, because this is sort of, let's say it's a weak rock situation, you need to have a good shape, and that was all done by laser survey. We actually used macrosynthetic fibers instead of steel fibers in some sections, and it's got the spray applied waterproofing membrane. What you can see here is the laser theodolites total station that was used to be controlling the shape. So there are no lattice girders at all here. We are also drilling spiles, so steel bars to protect the crown, because it's a 10-meter diameter tunnel, and you've got people. We try to remove people from the face as much as possible, but you can drill the spiles without having an arch. So the miners, of course, did not feel comfortable with that to begin with. But with modern equipment, you put the boom close to the face. It has a guide ring. So this was typically spiled here as well. And it's much safer than trying to put an arch up to the face where you have unstable ground. Now, the client's approach to innovation was, he wasn't sure. So we don't build a lot of tunnels in the UK. This is the first tunnel built by the Road Authority for probably 20 years. So they said, okay, it's a nice idea, but we want to have the two designs. We want to have a traditional design with cast in situ, double shell lining, classic NATM, shall we say. We want to have those two designs run in parallel. We'll excavate the tunnel, and then we'll have a look at how much water is coming in, and we'll think about, is it good to have this spray applied membrane? So the alternative design here has a spray applied membrane all the way around. But again, it's this question about what do you need a secondary lining for? So if you're in a road tunnel, you need it for visibility. As you drive, you want the white walls for the first 3-4 meters to give that visibility, the safety when you're driving. You want something you can clean quite easily. That's the primary criteria. So cast concrete sidewalls with no reinforcement, and then permanent spray concrete in the crown to cover the membrane. And of course, the initial lining here, the rock support, is permanent spray concrete. So this is the application of the spray applied membrane. As you can see, just progressively working along the tunnel. And then you have the casting of the sidewalls. They're coming up here from the road deck. Well, the final road will be above the first stage concrete. And that's how it looks at the end of the day. So a very high quality finish, very bright environment. So it just looks like any other road tunnel you can imagine. In the top, it looks black, which is the same as any other road tunnel, but a much more economic design. So it saved about 1% of the total construction cost of the project. It saved a lot of time, about 3 months on the overall program. And going back to some of the earlier points I made, a huge saving in the carbon footprint. But we were able to do that today. Well, I mean, okay, this is 10 years old. We're able to do it with technology right now. An easy change to make, much easier than any other way that you can think of to try and reduce the carbon footprint by 30%. So, apologies for overrunning. Too many things to talk about in this subject. But what I hope I've illustrated is that permanent spray concrete is proven technology. We have we have thousands of kilometers of tunnel built around the world, all around the world, with this technology. So we know we can produce high quality spray concrete as good as cast concrete. We have a variety of ways of dealing with waterproofing, because that's the next big question. We can remove steel bars and replace them with fibers, steel or non-steel, so we have a way to remove that durability problem. And this all opens up the path. If we change this design concept, we're able to reduce the carbon footprint. And that is something that we will be forced to do. It's not going to be our choice. It's going to come as a requirement very, very soon. That does require, and so if I may give a message to any clients in the room, it requires clients to be open to innovation, and that's a problem that we encounter in many places in the world. That people say, I have a rule book, I have regulations, it has to comply with this. We have to acknowledge that technology is always ahead of the rule book. And we have to look at what has been proven other places, and this is why we write these reports, to gather the information from different countries to show that it is reliable to use these technologies. So clients have to be open to innovation, and they also have to reward contractors for green solutions. That is the only way we're going to make progress to meet the ambitions or the requirements, shall we say, that government will give us, which is to reduce our carbon footprint. So I hope that has been helpful, and that concludes my presentation. Hvala vama.